Lights for me, please. Alright, example 8. Two identical collision cars, except for color, one is red, one is blue, are traveling in opposite directions. They collide and come to rest. How does this impulse apply to the blue car from the red car compare to the impulse applied from the red car to the blue car, and so on? You guys can read it. We'll come back to this. How does initial velocity compare? How do their change momentums compare? Yes, we are recording that. Right now. Right now. That was your question.
I think they should do.
Rex greets you all. Okay. So, red car and blue car, just like in the example, right? Just like when we talked about. Where's my clicker? Sorry for the delay, people with YouTube. I'm trying to find my remote control. Oh, there. My goodness. Okay. So, red car, blue car. I'm going to push them towards each other, and I'm going to push them at the same velocity. So, if they have the same velocity, what do we know about their momentums? They're the same, right? So here, red car, blue car, same velocity, hit.
Explode.
Yeah. So, what's the momentum right now? What's the momentum of these two cars right now? Zero. Right? So, the total momentum right now is 0. Right? So, what were their momentums before?
10.
So, which one's 10?
Both.
They're both 10.
They have the same velocity.
They have the same velocity, but they can't both be 10 because momentum has a...
One's in 10, one's negative 10.
Perfect. So, because they hit and stop, that means that their momentums, the change in momentums from one equals the change in momentum from the other, but opposite direction. We kind of talked about that a little bit on Friday. All right? But one has a momentum of positive 10 before, and one has a momentum of negative 10 before. Okay, now the 10s are just arbitrary, but Caleb's on the right track. That the momentums, the magnitudes are equal, but the directions are opposite. Does that make sense, guys? Yes. So, how do we get to momentum is 0? Now, as these two collision cars collide, what do you know about the forces they exert on each other?
Equal.
They're equal and opposite. How do you know that? How do you know that? Newton's third law. Good. So Newton's third law says that every action has an equal and opposite reaction, right? So when the two cars collide, the force of the blue car equals the force of the red car, right? Right? But what do we know about the directions? Are they equal?
Opposite. They're opposite.
They're opposite direction. Right? So we can say the blue one's going negative since the blue one is going... Actually,
No.
the red one's going left, so you probably want to make that one negative, don't you?
Yeah.
Okay. Does that make sense, guys?
Nope.
No?
Nope.
Why does it make sense?
I'm kidding.
You're kidding. I don't know if you're kidding or not.
Physics makes sense.
Okay. The reason why this is the case is Newton's third law.
Yep.
Okay. And our big snowball rolling down the hill collecting physics ideas is getting bigger still, isn't it? Okay. We brought Newton's third law with us. Now we're including that in momentum. It's kind of
So
cool.
did
all
Newton
together.
come up with all of this?
That's why they call it Newton's third law.
No, this
Yeah.
this idea too.
Yep. This is called Newtonian mechanics. What we're studying.
Is
Alright.
it really? Or did you just make that?
No, it really is. All right.
Why
Any
do you-
questions? Any questions about why those two forces are equal? Now, what do we know about the length of the collision for the two cars?
It's not a very long collision.
You sure? They're still colliding.
Oh.
Okay. What do you know about the length of the collisions? Omar, you're saying something? No, they're Velcro. Okay. So, when the two cars hit and collide, right? Even if they hit and bounce off each other, what do you know about the length of the collision for both cars?
Equal.
It's equal, right? It's the same.
It's all equal.
So I can, right on here, I can I can multiply both sides by delta t. And as long as we get the same delta t, we're okay, right?
You wrote this already.
Right? And then what do you know about their impulses? Equal. Except one is opposite. Perfect. And then because of that, we know that their change in momentums are also the same. But opposite. So, let's think about the collision cars. Thank you for separating them, Kyle. Okay. If we think about the collision cars, we know that because their force are equal, because their change in time is equal, we know their impulse are equal, right? Because their impulse are equal, we know their change momentums are. They're equal in magnitude, but opposite in direction. Perfect. So, if we look back at the collision cars. Okay. Okay, good. Everyone got negative again. So when I push them towards each other, when they hit, oh, blue one was a little fast to begin with. All right. We know their change in momentums are equal, but opposite in direction, right? So when the blue car comes in, it has positive momentum, right? So then when the red car hits it, the blue car, does it gain momentum or lose momentum? Loses. The collision takes away how much? We said it had 10 to start. It takes away how much from it then? 10. So the blue car experiences a negative 10 change momentum, right?
Yep.
The red car, remember Caleb told us earlier, because they hit and stop, their momentums have to be equal to start. The red car, when it hits the blue car, it experiences that same change momentum, that same negative 10, right? But the direction in this case is opposite. So does the red car get a negative 10 change or a positive 10 change?
Positive.
Positive 10 because the red car experiences a force this way. Does that make sense? Okay. Blue car felt the force this way, so it had negative change momentum. Red car experiences a force this way, so it has positive change momentum. Does that make sense? Yeah. So instead of subtracting 10 from the red car, we add 10 to the red car. So its negative momentum becomes 0, right? And the blue's positive momentum becomes 0. And when they hit, do they move?
No.
No.
They're not supposed to.
They're not supposed to, but sometimes Mr. Branch doesn't have a perfect starting velocity that can do it.
Who taught Newton physics?
He taught himself.
Wow.
Okay.
But who did
Any
he-
questions? He studied at Oxford before he actually came up with his 3 laws during the Black Plague break. He thought spring break was long. All right.
Good one.
So which one do you guys want me to add to mass to?
The red one.
That one. The red one?
Yeah.
So remember on Friday we did some scenarios like this, and we said the change in momentums were still the same because they were transferring velocities, right? And we did one like this, right? We did one like this. And we said the change momentums are still the same because it seemed like they were just transferring velocities back and forth. You guys remember that? Okay. You want to add momentum to the red one, you guys, or mass to the red one, you guys said?
Yes.
Okay.
That's a
So
lot of mass.
now what happens if I do this? What happens?
It experienced a lot more.
So when we're talking about the force, you can stand up with me. It's fine. Okay. Okay. Now, who's experiencing a greater force?
Blue. Wait, no.
But why does the red keep moving?
Blue. It's equal and opposite.
It's not
Right, you took the
equal.
sucker bet.
It's
Okay.
equal and the red car will stop moving.
Okay. So a lot of times when students see this demonstration, they say, "Oh, the blue one experiences a greater force. It goes so much faster afterwards, right?" But the same rules we just figured out still apply.
Oh, never mind.
Okay? Guys, the same rules we just talked about still apply. Newton's third law still applies. Still applies. Reggie, paying attention or what? All right, picture. All right. Newton's third law still applies. All right. The blue car and red car apply the same force to each other, which means they have the same change in momentum, right? But the blue car goes away with a much larger velocity because it has less mass. Not less momentum. Has less mass. Okay? So, think about it this way. Let's say the red car has, give me a number.
6.
-6. Okay. If the red car comes in with -6 and hits the blue car, is the blue car getting all of that -6?
No.
No. It might be getting like 5 of that -6 because what does the red car still do?
Move.
Keeps moving, right? So the red car comes in and hits it. The red car keeps going, but the blue car gets majority of the momentum, right? And the blue car goes off at a much faster velocity because it has less mass. Okay, does that make sense? Let's look at this scenario the other way. Let's do this. The red car still has more mass, okay? Here comes the blue car. What happened there?
The blue car still got the
Are they still applying equal forces to each other?
Yeah.
Yeah.
They still applying equal forces to each other?
Yes.
Of course.
Yeah.
No.
Nothing gets the majority. Okay. So what does the blue car have to start? Give me a number. 5. Okay. If the blue car starts out with 5 kilograms meters per second of momentum, when it hits the red car, when it hits the red car, right? The red car then goes this way at a slower velocity than the blue car, right?
Yep.
Because the red car has more
Mass.
mass. And the blue car bounces back, doesn't it?
Yeah.
Okay. So, do you guys think the total momentum of the red car is more or less than 5?
10.
More.
More. And Monty and Terry, why do you say more? Monty, you go first. Why do you say more?
Because it makes it move.
Because it makes what move?
Less. I meant.
No, you didn't. You meant more. Okay. Terry, why more?
Because the red car has. What was the question again?
Yeah, what was the question?
You said more, we don't know the question.
I forgot.
Okay. So right now we said the blue car has 5, right? When the blue car is 5 kilograms meters per second of momentum, right? When it hits the red car, does the red car have more or less than 5?
It has more.
Less.
It has more.
What is less than 5?
It has more.
What?
Terry, why do you say more?
Because it has more mass.
Nope.
Oh.
It's less because
Good try though.
Less mass.
the,
Equal?
the car, the blue car transferred.
Inertia.
I am.
The blue car transferred its momentum to the red car, and the red car is moving slower than the blue car is moving.
Remember, the red car has more
Mass, but
Mass.
still moving slower.
So if they have equal momentums, right? The red car has to move slow, right? Right?
Yes.
Okay. So Terry, you're right. The red car does have more. Lau, you want to try?
I think I know why.
What?
Because the blue car comes in with 5 kilograms meters per second, hits the red car, but the blue car is moving back, which means that the red car applied more force than the blue car hit it with.
Didn't apply more force. The forces are equal, right? That's their
Momentum.
law. You're on the right track though. The blue car bounces back, right? So the blue car had 5 positive, right? When it bounces back, we could say it has
4 negative.
4 negative.
0 negative.
Okay, that's a lot, but we'll go with that. So what was the change in momentum of the blue car? It went from 5 positive to 4 negative.
Why can't we say -4?
Okay. Went from 5 to -4. What's the change? -9. Perfect. So if the blue car experiences a change of -9, that means the red car has to experience a change of
Positive.
Positive.
+9. Equal and opposite, right?
Yes.
So that means when the blue car hits the red car, since the red car was at rest, if it gets +9 kilograms meters per second, what happens to it?
Because momentum.
It gets momentum and starts moving, doesn't it? +9 was bigger than the 5 the blue car came in with, wasn't it? So the red car has more momentum than the blue car at the end, but combined, it still equals how much?
Equal.
Remember we said 5 and 0, right? It's 9 negative and 9 positive. No. 4. Oh, you're right. -4. Thank you. I should write things down. -4, right? And 9. So what's -4 and 9 add to?
10.
What's -4 and 9 add to?
13.
5.
Thank you.
You're welcome.
13, really? -4 and 9. Use your calculator next time. All right. So comes in with 5. 5 plus 0 is
5.
5. Good. Nice job. Okay. Bounce off. Caleb, I was giving you redemption right there.
What?
Okay. +9. +9. -4.
6.
What do they add to?
13.
Oh my gosh. They added 5. So we had 5 before and 5 after. That's something we should hold on to for our next topic. So, talking about these questions. How does the impulse apply from how does the impulse from the blue car and red car compare to each other?
Equal.
Equal and opposite. Good. B. How do the initial velocities compare? Well, if their masses are the same and they hit and stop, right? We know their initial velocities had to have been equal, right? Because the change momentum is the same. C, how does your change momentum compare? Equal. Okay. Now, how does the previous example change if we double the mass of the red car?
It doesn't.
It doesn't?
It's still equal and opposite.
Okay, well, let's try.
No.
I will send them towards each other with the same velocities, and we'll see if they hit and stop. Gotta put the pistons in. The pistons, like the ones from Detroit who don't play basketball anymore.
The red one's gonna open.
Okay, you guys ready?
Keep going.
Same starting velocities. Here we go.
Oh, let's go.
What happened?
He took it
Oh,
with him.
what? Do it
The
again.
red pushed it this way, right? We'll stop playing with the stapler and pay attention then.
He said you're not.
Ready? Okay. Same starting velocities. They end up going in the same direction as the red one, right? Right? Because the red one has more momentum.
But
So we have more momentum going in this direction, so when they hit it keeps going in that direction. That's something we'll talk about later, but
they
it's
don't
something
have
we
the
talk about
final.
right now.
The same
Alright,
final.
so
it's
in
not-
order for these two to hit and stop, they need to have the same exact change. Well, they have the same exact change momentum anyway, right? But they need to have the same momentum to start, don't they?
Yeah.
So in order to have the same momentum to start, that means the red one has to have a velocity that is slower than the blue one. Okay? So let's see. I'll try one try. Caleb, stop playing my staple. Put it down. Okay? So here we go. No. Okay, last try. I can do this all day anyway. No!
Wait,
Okay.
wait. Have somebody else do it.
No. This is my video. Just joking. Ah, I'll give it up. All right. But you guys get the idea. Yep, I'm recording it.
I
Hold
can
on.
turn it
Let
off.
me push the blue one and you push the
No,
red.
that's fine. You guys get the idea, though. In order for them to hit and stop, they had to have the same momentum to start, right? So their change in momentums had to have been the same. In order for them to have the same momentum to start, since the red one has twice the mass, the blue one has to have louder, Cheyenne. Twice the velocity. Perfect. So how do their change momentums compare then? How do their change momentums compare? Come on, guys, we're just being in class. How does their change momentums compare?
They're equal.
They're equal. During any collision, their change in momentums are the same. Because of Newton's third law. Alright? Alright, any questions? Any questions?